what comes to the next section? Having done the Laplace transforms, we'll go ahead today and look at the inverse Laplace transform. And I explained to you why we need the inverse Laplace transform. Because originally we're in the time domain, we moved to the frequency domain. So if we are moving back to the time, we use the inverse Laplace transform. This is just the Laplace transformation. And this is going to be helpful if you can, should I use the word memorize, or be able to compute the Laplace transform of the common functions. So I'll do it on table. The table I have in slide 10. You realize that the Laplace transforms have been given. It means that the Laplace inverse of 1 on s should give me 1. Laplace inverse of 1 over s minus a should give me my EAT. I'm moving backwards. Laplace inverse of n factorial over Sn plus 1 should give me my Tn. Laplace inverse of s over s squared plus a squared should give me what? My cos At. And all the others. So the inverse should give you whatever you had in the original transformation. Now the question is, how do I solve for this? Assuming that these common functions are not here. Assuming I don't know this common. In a case where these common functions are not given, how do I then solve for the inverse Laplace transform? We go by a technique called partial fractions. I'm sure some of you will smile hearing this because it's something you've done in your calculus 1. Partial fractions. The idea is you have some rational functions or expressions and you want to simplify them into some forms. This is some P on Q, and depending on what Q is, whether it is a linear factor, it is a repeated linear factor, or it is it complex? No. What linear repeated, is it quadratic? Yeah. So if it's linear, you know you have it as a over whatever term you have. If it's repeated, I have a over the first term plus b over the term to the power 2 plus c over the term to the power 3 through to z over the term to the power n. If it's quadratic, I have it as ax plus b over the terms I have in Q. So let me just say a over Q over Q. Yeah, this is fine. And there's, before you can use partial fractions, you must check the degrees of the numerator. If the degree of p is less than means this way. If it's less than degree of q, you can use the partial fractions. Other than that, you must go through the long division approach of polynomials to arrive at your answer. So I'll quickly take an example each under these 3. Forgive me, this might be a long video because I'm going to take all the examples as a goal. So let me take the first one. Sorry for that. Let me take example on a linear factors or linear factors. That is fine. Assuming I have a function of in the frequency domain given as s plus 1 all over this. Now the degree here is 1. The highest order is 1. The degree here, if I should expand this, you realize the degree here is 2. Now 1 is less than 2, so I can go ahead and use the partial fractions. Because I want to find ut, the question is what is ut in time? It means I have to take the Laplace inverse. So Laplace inverse of u of s is going to give me the Laplace inverse of every term here. And because this is a linear root, this is linear, this is linear, It means this is the same as a on s plus b on s plus 2. So Laplace inverse of s plus 1 over s plus 2 is the same as Laplace inverse of these terms. What do? I can take the LCM here, and a takes s plus 2, b take s. I'm going to compare these ones. I can expand. If I expand and compare coefficient, this partial fraction, so I wouldn't go through the details. If I expand, I'm going to get a plus b equating to 1, the coefficient of s. And if I take the constant part, I'm going to just get 2a equal to 1. From this equation 2, we realize a is half. From this equation, b is going to be 1 minus a. So 1 minus half is still half. It means I'm looking at the Laplace inverse of 1 over 2s plus 1 over 2s plus 2. I did a substitution of these ones into that. If I factorize 1 over 2 out, I'm going to get Laplace inverse of 1 on s plus 1 over 2 out, Laplace inverse of 1 over s plus 2. Now look at the table. What is the Laplace inverse of 1 over s? You realize that it is 1. Laplace inverse of s plus 2. It can only be from the exponential function, given that a is equal to negative 2. Because Laplace of EAT is 1 over s minus 2. And so if a is negative 2, I'm going to get this one. It means I have it as this. And this is my u of t. Now there's no more terms in s, there are only terms in t. So Laplace inverse of all the u in frequency is just half plus this. Someone may be wondering, how do I know my solution is correct? What do? You must find the Laplace transform of the ut. It's no more the inverse, but then the direct transformation. What's the Laplace transform of half? Laplace transform of e negative 2t. You realize that you're going to get the us. You can try this out. Okay. The second example, let me take a clean sheet. I've done the linear roots. Let's take repeated roots or factors. Assuming I have a frequency domain given as s squared plus 1 over s squared s plus 2. The degree here is 2. The degree here is 3. If I expand, 2 is less than 3. Hence, my partial fractions should work. Now over here, there are two ways to solve this one. This is repeated. And then this is a linear straight factor. So I can write that. It means this is the same as Laplace inverse of the repeated takes a over the first term. This partial fractions, I repeat that, plus another term for the squared is repeated. Then c plus the last linear term. This is what I have. So it means I'm going to compare s squared plus 1 as a taking s and then s plus 2. I'm going to take b to be s plus 2, and then c takes s squared. Why do I get that? If I find the LCM here, you know we have to compare the numerators. So there's no s here. There's s because a is over s, so it takes one s out here. So that's what I have. So I have to compare the numerators here. You know, there are several approaches of doing this. You can easily eliminate, or you can expand and compare coefficients. If I'm going to expand this, I'm going to get ax squared plus 2as plus bs plus 2b plus cs squared. And comparing that of the s squared coefficient, it means my a, so this and then c should give me 1. The coefficient there is 1. If I compare those of s only, I'm going to get 2a plus b should give me 0 because there's no term of s in this form height. If I compare the constants, that means I'm going to get just 2b to be equal to 1. From here, I know my b is half. Then I can find a from here. A is negative b on 2. And what do I get for that? That'll be negative 1 on 4. And then from here, I can simply find c as 1 minus a. 1 minus 1 minus 4, what do I get? What do I get? I get 5 on 4. So it means that Laplace inverse of a on s, is it s? Let me check. Yeah. Plus b on s squared plus c on s plus 2 is equal to the Laplace inverse of a is negative 1 over 1 over 4 s plus 1 over 2 s squared plus 5 over 4 s plus 2. So on the table here, you realize that if I factor 1 over 4 out, I'm going to get Laplace inverse of 1 on s. If I factorize the constant half here, I'm going to get Laplace inverse of 1 over s squared. If I factorize 5 on 4 as a constant, it is 1 over s plus 2. Now, from the table, what are these inverse Laplace transforms? I'm going to get this to be 1. This is going to be t squared, because t to the power n is n factorial over s n plus 1. So if I'm getting 1 over s squared, it means n is equal to what? 1. So it's times t. And then the last one, is it cos or an exponential? It's an exponential function, negative 2t. So you do a cross check on your table. This is not cos, it is not sine, it is not exponential, because they don't take that form. They only take the t to the power n form from the table. Okay, and so this is my u, or f of t. So my time domain is 1 over 4 plus 1 over 2t plus 5 on 4 exponential. This is the final answer. Please take your time and do the Laplace transformations or the partial fractions. The last example, let me take another sheet. We've done linear, we've done repeated. Let's take the quadratic root. And so assuming I have a frequency domain given us, okay, please always don't forget to check the degrees before you just go straight and then simplify. The mistake some of you will do is, I know there's a quadratic root, so I'll simply say this is some ax plus b over all these terms. Please, when you do that, it is wrong, because you've not checked if you can use partial derivatives. Sorry, partial fractions here. You must check that before you go ahead. So then I'm going to undo So let's do the checking. The degree here is 2. The degree for the denominator is also 2. Can I use the partial fractions here? No, because they are equal. If it's strictly less than, I go. If it's greater than or equal to, it is no. I can't use the partial fractions. The only way to use it is to get it in a degree that satisfies that, and that's the long division approach. So I want to divide s squared, no. So with the long division approach, I have 3x squared plus 2s plus 3. This taking s squared plus 3s plus 2. What will be the factor here? The factor here will be 3. So what I get 3s squared plus 9s plus 6. I subtract. This is going to give me negative 3. 3 minus 6, negative 3. 2 minus 9. That's negative 7s. And this part is 0. Can I move further? No. That is it. I can't move further because the degree here is just 1. This is x squared. And how do we write this? We write the root plus the remainder over the quotient or the divisor. So s plus r over q. What is my s? My s is 3. My remainder is negative 7s minus 3. My divisor is 3s squared plus 9s plus, oh sorry, the divisor was s squared plus 3s plus 2. This is the new frequency domain I must simplify, not the original one, because the original one I couldn't use partial fractions on. So let's check again. Can I use partial fractions here? What's the degree of the numerator? It is 1. Degree of the denominator, it is 2. Voila, I can use partial fractions. So Laplace inverse of 3 plus negative 7s minus 3 all over this is given as Laplace inverse of 3 plus, this is now partial terms. It is, there are two ways to solve this part. Either you use a cubic as ax on b, over whatever you have here, or I can have the linear form as a over some s plus 1 and then b over some s plus 3 if I'm correct. It means that these two things should give me this quadratic, which is true. So either way you solve, it is still solving for a and b, but I prefer the linear approach. It is easier to solve in that state. Okay, so let's see. Which ones am I comparing? My 3 is standard. So I have the LCM to be s plus 1, s plus 3. It means a is going to take s plus 3, and then b is going to take s plus 1. I'm comparing these ones. My 3 is already in its right state. I have to find a and b. If I want to compare coefficient, realize that if I expand as plus 3a plus bs plus b, I'm going to get a plus b equated to negative 7, and then 3a plus b equated to negative 3. If you solve this variable, you should get a to be, a should give you 4 and then b should give you 11. You can check that. Negative 11 plus 4 gives you negative 7. This is what you're supposed to get. It means that finally I can represent this as Laplace inverse of 3 plus 4. A is 4, so 4 on 3, s plus 1. B is negative 11 on s plus 3. Now over to you. What is Laplace inverse of 3? If I bring my constant 4 out, what is Laplace inverse on 1 over s plus 1? If I take my negative 11 as a constant out, what is this one? Are these ones exponentials? Are they t to the power n's? Are they cos or sines? You agree with me that it is exponential. Negative t, exponential, negative 3. That's the only way to get the positive signs. Now the last thing is, what is the inverse of 3? Do we know this? Kindly find out. Don't say it is 3, because Laplace of 1 is 1 on s. Hence Laplace inverse of 1 on s is 1. But here we are looking at Laplace inverse of 3. It is not 3 on s. If it's 3 on s, I'll say it is 3. But it is the inverse of the 3 itself. What is it? So kindly find out and then add it to your solution. And this is how we find the Laplace inverse of given functions. Kindly take time and then go through. In my last 2 videos for Laplace transforms, I'm going to consider Laplace transform for derivatives and then Laplace transform for solving the differential equation. Until we know this, we can't look at that. So stay tuned for the last 2 videos under Laplace transformations. Thank you very much.